Hello, and welcome back to the Sleepy Darwin. Whether you're here to let the weight of the day slowly dissolve, to find some peace in the quiet hours, or to simply listen to the gentle rhythms of our living planet, you've found your sanctuary. Tonight, we're embarking on a soothing journey into one of the most remarkable stories ever told. The story of how our Earth, like a patient gardener tending to herself, quietly mends what's broken, cleanses what's polluted, and nurtures life back from the very edge of extinction. From the slow, ancient breathing of forests regenerating after wildfire to the patient work of rivers carving new paths around human scars, tonight we'll explore the tender, persistent ways our planet heals itself. And yes, we'll discover that she's been doing this long before we arrived, and will continue long after we're gone. Before we begin this gentle descent into geological time and natural restoration, if you find comfort in these quiet explorations of science, a like and subscribe would mean the world to me, quite literally, in this case. And please, let me know in the comments where you're listening from tonight. Are you in a bustling city learning to breathe again? Or somewhere rural, where you can already hear the Earth's quiet work happening outside your window? I'll do my best to keep this journey calm and restorative, but fair warning, our planet's resilience is genuinely awe-inspiring. I hope this isn't so fascinating that it keeps you wide awake, but if it does, at least you'll drift off knowing that beneath your feet, ancient systems of renewal are working their quiet magic. So settle in, let your shoulders drop, and tonight, let's listen to the Earth's own lullaby of healing. Now, let's begin with something that might seem a bit strange to talk about while you're settling in for the night. We're going to explore the idea of endings, but not the kind that leave you feeling hollow or afraid. These are the endings that make space for entirely new beginnings, the kind that clear the stage so completely that what comes next is almost unrecognizable from what came before. You see, extinction is happening all around us, all the time. Right now, as you listen to these words, somewhere on Earth, the very last member of some small, unknown species is taking its final breath. This has been true for every moment of every day, for the past 4 billion years. It's what scientists call background extinction, the quiet, constant drumbeat of species saying goodbye to the world, usually one at a time, often so gradually that the change is barely noticeable. Think of it like books disappearing from a vast library. Every so often, a single volume vanishes from the shelves. Maybe it's a rare poetry collection that no one has checked out in decades, or a manual for some obsolete piece of machinery. The library remains fundamentally the same. The stories continue. Life goes on. But sometimes, maybe 5 times in Earth's long, long history, something far more dramatic happens. Instead of losing single books here and there, entire wings of the library go dark overnight. Entire sections vanish. Fiction, science, history, philosophy gone, leaving behind only empty shelves and the faint scent of what used to be. These are what we call mass extinctions, and they are among the most humbling chapters in the story of life on Earth. The scientists who study these events have identified what they call the Big Five. 5 moments when life came so close to ending that it's genuinely miraculous any of us are here to contemplate them. These aren't just scientific curiosities buried in academic journals. They are the intermissions between Earth's greatest acts, the moments when the stage went completely dark before the next performance could begin. And here's something that might surprise you, something both unsettling and oddly comforting. These catastrophic endings seem to follow a rhythm. Every 26 million years or so, give or take, something goes terribly, catastrophically wrong. The pattern is so consistent that it's almost like Earth has some cosmic alarm clock set to apocalypse. Though what sets off that alarm remains one of our planet's most beautiful mysteries. Some scientists think it might be related to our solar system's orbit through the galaxy, periodically carrying us through regions dense with comets or cosmic debris. Others wonder if there are cycles in Earth's own geology, massive volcanic episodes that build and release over millions of years, like some planetary respiratory system. But whatever the cause, the pattern persists. Every few million decades, life faces a test so severe that most of it fails. Now, I know what you might be thinking. This doesn't sound very relaxing. Why are we talking about the end of the world? But here's the thing that makes these stories so remarkable, so worth contemplating as you drift towards sleep. Every mass extinction in Earth's history has been followed by an explosion of creativity, diversity, and beauty that surpasses what came before. The endings, as profound and tragic as they are always followed by beginnings so magnificent that they justify the darkness that preceded them. But before we explore those specific stories, let's pause for a moment and try to wrap our minds around the sheer scale of time we're discussing. This is important because without understanding deep time, mass extinctions feel either insignificant or terrifying. With the proper perspective, they become something else entirely. They become chapters in the most epic story ever told. Imagine, if you will, that all of Earth's history, all 4.5 billion years of it, could be compressed into a single 24-hour day. Picture yourself watching this day unfold from some cosmic vantage point, seeing the entire story of our planet play out from midnight to midnight. The Earth forms at the stroke of midnight, a molten ball of rock and metal slowly cooling in the darkness of early morning. For the first few hours, representing the first billion years, our planet is a hellscape of lava and bombardment from space, utterly hostile to anything we would recognize as life. But around 4 in the morning, something magical happens. The first simple cells appear in the ancient oceans. These aren't anything fancy, just tiny bags of chemistry learning to copy themselves, but they represent the moment life first whispered its presence in the cosmic darkness. For most of the day, from 4 in the morning until about 8 at night, life remains microscopic, invisible to the naked eye. Bacteria and their slightly more complex cousins, the archaea, rule the world. They're busy doing the most important work in Earth's history, learning to eat sunlight, breathe oxygen, and transform the very chemistry of the planet. But if you were watching from space, you wouldn't see much happening. Around 8 in the evening, things get interesting. Complex cells with nuclei appear, the ancestors of every plant, animal, and fungus you've ever seen. An hour later, around 9 o'clock, the first animals show up. Strange, soft creatures that look like nothing alive today, drifting through the ancient seas like living abstract art. At 10:30 in the evening, life explodes into the forms we're more familiar with. Fish with backbones, early plants colonizing the land, insects taking to the skies, the first forests spread across the continents. The dinosaurs rule from about 11 o'clock to 11:40. In this cosmic day, their entire 165 million year empire lasts about 40 minutes. The asteroid that ends their reign falls at 11:40 in the evening, and mammals, our ancestors, inherit the Earth. And humans? Modern humans appear in the last few seconds before midnight. All of recorded history, everything from the pyramids to the internet, happens in the final fraction of the last second of the day. From this perspective, mass extinctions aren't aberrations or mistakes. They are part of the natural rhythm of deep time, moments when life pauses, takes stock, and then explodes into forms more beautiful and complex than anything that came before. The fossils that tell us these stories are themselves monuments to patience. Every bone, every shell, every leaf impression preserved in stone represents a moment when some small piece of life was buried so quickly and perfectly that it could wait millions or hundreds of millions of years to tell its story. They are messages from the deep past, postcards from worlds so alien that we can barely imagine them, yet connected to us by an unbroken chain of survival, adaptation, and the stubborn persistence of life itself. Now, when scientists talk about mass extinctions, they often speak in percentages that can sound abstract until you really think about what they mean. 90% of species vanished. 75% of all life disappeared. These numbers can slide past us like any other statistic, but they represent something almost unimaginable. Imagine walking through a forest, anywhere on Earth. Picture the trees, the birds singing in the canopy, the insects humming in the undergrowth, the small mammals rustling through the leaves, the fungi quietly decomposing fallen logs, the bacteria in the soil, the lichens on the bark. Now imagine that 9 out of every 10 forms of life in that forest simply stopped, vanished, not moved somewhere else, not evolved into something different, but gone completely, leaving behind only empty spaces in the web of life. This is what 90% extinction means. It means walking through a world where the silence is so profound, so complete, that it becomes a presence unto itself. It means ecosystems collapsing like houses of cards, food webs unraveling, and the survivors, that miraculous 10%, suddenly finding themselves in a world where all the rules have changed. But here's the thing that makes these numbers more than just tragic statistics. That 10%, that tiny fraction of life that survives, carries within it the seeds of everything that comes next. In the mathematics of survival, a single breeding pair can, given enough time, become millions of species. A small population of mammals, huddling in burrows after the asteroid impact, carries within its genes the potential for elephants and whales, for primates and humans, For bats that navigate by sound and dolphins that communicate in languages we're only beginning to understand, the mathematics of mass extinction are also the mathematics of explosion, not just the explosions that cause the extinctions, but the evolutionary explosions that follow them. Each catastrophe clears ecological space, removing the established players and opening niches for evolutionary experimentation on a scale that would be impossible in a fully populated world. After the Permian extinction, the worst of all the mass extinctions, life took nearly 10 million years to fully recover, but when it did, it came back with dinosaurs, with the first mammals, with flowering plants and flying insects. The world that emerged from that catastrophe was more beautiful, more complex, and more diverse than anything that had existed before. After the asteroid impact that ended the dinosaurs, mammals exploded into forms that would have seemed impossible in the age of reptiles. In just a few million years, the blink of an eye, in geological terms, tiny shrew-like creatures gave rise to giants like Uintatherium, with its strange horned skull, and early whales that still walked on land with legs they would soon lose to the sea. This is the poetry hidden in the percentages. Every mass extinction is also a mass liberation. Every ending enables beginnings that would have been impossible under the old regime. The mathematics of survival are brutal, yes, but they are also the mathematics of infinite possibility. Life, it seems, has a way of making the most of catastrophe. It takes the broken pieces of destroyed ecosystems and assembles them into something new, something often more intricate and beautiful than what was lost. It's as if each mass extinction is life's way of asking itself, what else is possible? What new forms might emerge if we cleared the stage completely and started over? And the answer, every time, has been more than we could have ever imagined. As you lie there tonight, breathing slowly, letting these vast stories wash over you like gentle waves, consider this. You are part of that answer. Every cell in your body, every thought passing through your mind, every dream that will visit you tonight is part of life's ongoing response to catastrophe. You are what becomes possible after the world ends and begins again. The mass extinctions that we'll explore together in the coming chapters are not just ancient history. They are the reason you exist, the crucible in which consciousness was forged, the dark spaces between notes that make the music of life so hauntingly beautiful. So let's continue this journey together, moving slowly through deep time, visiting those moments when everything almost ended and somehow, miraculously, didn't. Let's explore the rhythm of endings and beginnings, the patient way life learns from catastrophe and grows stronger, stranger, and more wonderful than before. Because that rhythm is still playing, even now, even as you drift towards sleep. And you, dear listener, are part of its most beautiful movement yet. Let's drift back now, much further back than our minds are used to traveling. We're going to visit a world that existed 252 million years ago, a world so different from ours that it might as well be another planet entirely. This is Earth during the Permian period, and if you could somehow step through time and walk across its landscapes, you would find yourself in a place both wonderful and utterly alien. There were no mammals yet, no dinosaurs, no flowers blooming in meadows or birds singing in trees. The world belonged to creatures whose names sound like incantations from some ancient spell. Gorgonopsids, Dinocephalians, Paraeosaurs, these were the rulers of the Permian Earth, and their reign was about to end in the most catastrophic extinction event our planet has ever known. Picture, if you can, a single enormous continent called Pangaea, stretching from pole to pole like a vast irregular landmass floating in a global ocean. All of today's continents were pressed together into this supercontinent, creating climates and weather patterns unlike anything we experience today. The interior of Pangaea was a vast desert, dry beyond our imagination, while the edges were lined with swamps and shallow seas teeming with life. In those ancient waters, coral reefs built intricate cities beneath the waves. But these were not the corals we know today. These were rugose and tabulate corals, with geometric patterns so precise they look like the fossilized mathematics of some alien civilization. Swimming among them were creatures that challenge our very notion of what life can become. The trilobites, those remarkable arthropods that had ruled the seafloor for nearly 300 million years, were still there, though their great age was showing. They had survived multiple mass extinctions already, adapting and evolving through crisis after crisis. But they had no way of knowing that their time was finally running out. Some had developed elaborate spines and horns, others had grown enormous compound eyes that could detect the faintest glimmers of light in the deep ocean. They were the living libraries of ancient genetic wisdom, carrying within their bodies the memory of Earth's earliest experiments with complex life. But perhaps most remarkable of all were the synapsids, the early relatives of mammals that we sometimes call mammal-like reptiles, though they were neither true mammals nor true reptiles, but something wonderfully in between. There was Dimetrodon, with its magnificent sail-like back fin that caught sunlight like a solar panel, helping regulate its body temperature in ways that foreshadowed the warm-blooded metabolism that would eventually give rise to us. There were the Gorgonopsids, fierce predators with saber teeth and forward-facing eyes, hunting in ways that wouldn't look out of place in the African savanna today. On land, the first great forests of seed-bearing plants swayed in ancient winds. These weren't the flowering forests we know, but vast stands of seed ferns and early conifers, creating the first true woodland ecosystems our planet had ever seen. In the understory, early reptiles no bigger than lizards scurried through fallen leaves, while larger herbivores browsed on plants that had no names, because flowers hadn't been invented yet. This was a world in its prime, a world that had taken nearly 4 billion years to create, where life had finally learned to colonize both land and sea with equal success. The Permian period represents in many ways life's first great flowering into the modern forms we recognize. If you had been an alien biologist visiting Earth 252 million years ago, you might have concluded that life had finally figured itself out, that the experiments were over and the stable, mature phase had begun. You would have been catastrophically wrong. Deep beneath what is now Siberia, something was stirring that would change everything. The Siberian traps, as geologists call them today, represent one of the largest volcanic events in Earth's history. But calling them volcanic is like calling a hurricane breezy or an ocean damp. What happened in Siberia 252 million years ago was volcanism on a scale that defies our everyday understanding of the word. Imagine, if you can, a volcanic eruption the size of Europe. Not a single mountain exploding, but an entire subcontinent beginning to bleed lava and poison gas into the atmosphere. For 1 million years, a million years, these eruptions continued, pouring out enough molten rock to bury the entire continental United States under a layer of basalt half a mile thick. The sound alone would have been audible halfway around the world, a constant rumbling that lasted longer than our entire species has existed. But it wasn't just the scale that made these eruptions so devastating, it was what they carried with them. As the magma rose from deep within the earth, it passed through vast deposits of limestone and coal, vaporizing them and sending their contents into the atmosphere as greenhouse gases. Carbon dioxide, methane, hydrogen sulfide, and clouds of toxic compounds poured into the sky like the exhalations of some planetary fever. The very air became poison. You see, what was happening to Earth was something like what happens to us when we run a dangerously high fever. The planet's temperature regulation system was breaking down, and the normal mechanisms that keep climate stable were failing one by one. The ocean began to warm, which released more carbon dioxide from the water, which warmed the atmosphere, which warmed the ocean further, in a runaway cycle that fed on itself like wildfire feeding on wind. The oceans, those vast blue refuges that had harbored life for billions of years, became acid baths. The pH dropped so dramatically that anything with a calcium carbonate shell, the trilobites, the corals, the countless tiny plankton that formed the base of the food web began to dissolve. Imagine vast coral reefs simply melting away like sugar sculptures in the rain, leaving behind empty underwater deserts where once there had been cities of life. On land, acid rain fell from skies the color of rust and sulfur. Plants died en masse, their leaves burned by chemical precipitation that was more like battery acid than anything we would recognize as rain. The great Permian forests withered and fell, creating vast landscapes of dead wood that stretched to every horizon. But perhaps most insidious of all was what happened to the oxygen. As plants died and decomposition accelerated in the warming world, the very air began to change its composition. Oxygen levels, which had taken billions of years to build up in the atmosphere, plummeted. The air became thin, difficult to breathe, insufficient to support the complex metabolisms that had evolved over hundreds of millions of years. The fever lasted for thousands of years, long enough for ecosystems to collapse completely, for entire branches of the tree of life to wither and disappear. By the time it was over, the planet had lost 96% of all marine species and 70% of all terrestrial vertebrates. To put that in perspective, if this extinction happened today, we would lose not just the pandas and the tigers and the elephants, but virtually every mammal larger than a mouse. We would lose not just some fish, but but 19 out of every 20 species in the ocean. The silence that followed the Great Dying was unlike anything Earth had experienced since life first colonized the planet. Vast stretches of ocean contained almost nothing larger than bacteria. On land, ecosystems that had taken hundreds of millions of years to develop were reduced to simple communities of fungi, ferns, and the few small vertebrates that had somehow managed to survive. Those survivors are worth contemplating as you settle deeper into comfort tonight. They were not the strongest or the most complex forms of life. They were not the apex predators or the most successful species. They were, in most cases, small, humble creatures that had learned the ancient art of making do with very little. Among them were the early archosaurs, ancestors of both dinosaurs and crocodiles, who survived by being generalists rather than specialists. They could eat almost anything, live almost anywhere, and required relatively little oxygen to keep their simple metabolisms running. In the post-apocalyptic world of the early Triassic, these modest reptiles found themselves inheriting an empty Earth with unlimited room for expansion. There were also the cynodonts, advanced synapsids that carried within their genes the blueprint for mammals. They survived by becoming smaller, developing more efficient metabolisms, and perhaps most importantly, by learning to burrow. Underground, they could escape the worst of the surface catastrophes, emerging only when conditions allowed. Some of the survivors were plants that had learned to reproduce without elaborate sexual displays, spreading by spores and simple seeds that could lie dormant for years until conditions improved. Fungi, those patient decomposers, actually thrived in the post-extinction world, feeding on the vast quantities of dead organic matter left behind by the catastrophe. But perhaps the most important survivors were microscopic, the bacteria and archaea that had been quietly maintaining Earth's basic life support systems for billions of years. They weathered the Great Dying much as they had weathered countless smaller disasters, by being incredibly small, incredibly simple, and incredibly persistent. What we learn from studying these survivors is that endurance in the face of catastrophe often has less to do with strength or complexity than with flexibility and humility. The creatures that made it through the Great Dying were those that could adapt quickly, live simply, and find opportunity in the spaces left empty by the departed giants. And here's the remarkable thing. Within just a few million years of the extinction, life was already beginning its greatest experiment yet. Those humble archosaur survivors would give rise to dinosaurs, creatures more magnificent than anything the Permian world had produced. The small mammal-like survivors would eventually evolve into true mammals, and eventually into us. The simple plants would learn to bloom, filling the world with flowers and fragrances that would have seemed like pure magic to any Permian creature. The Great Dying, as terrible as it was, cleared ecological space for evolutionary innovations that would never have been possible in the crowded, established ecosystems of the Permian. It was as if life, having grown perhaps too comfortable in its success, needed a profound reset to unlock its next level of creativity. The numbers from the Great Dying whisper to us across 252 million years, but they don't whisper of hopelessness. They whisper of the extraordinary resilience hidden in the simplest forms of life, of the way catastrophe can become opportunity, of how the darkest chapters in Earth's story often lead to the most beautiful ones. If you had visited Earth just a million years after the Great Dying, you would have found a planet that looked almost lifeless, dominated by simple fungi and scattered populations of small survivors. But if you had looked more carefully, you would have seen something remarkable. Those survivors were already beginning to diversify, to experiment, to explore the vast empty niches left behind by the extinction. You would have been witnessing the earlier stirrings of the Mesozoic era, the age of dinosaurs, the time when life would achieve a complexity and beauty that surpassed even the Permian world. You would have been watching the seeds of the modern world germinating in the ashes of the old. The trilobites were gone forever, ending their 270 million year reign as Earth's most successful arthropods. The great mammal-like reptiles had vanished, leaving behind only small descendants that would take a very different evolutionary path. The vast coral reefs had dissolved into chemical memory, but in their absence, new forms of life were already stirring, carrying within them possibilities that the Permian world could never have imagined. This is what makes the Great Dying more than just the worst catastrophe in Earth's history. It is also the crucible in which the modern world was forged, the dark intermission between Earth's ancient act and its most spectacular performance yet. Every dinosaur that would ever walk the Earth, every mammal that would ever draw breath, every flower that would ever bloom, all of them owe their existence to the small band of survivors that somehow endured when 96% of life disappeared. As you drift tonight toward your own daily intermission between consciousness and sleep, you might consider the cosmic stubbornness of life that carried our ancestors through the great dying. In your cells, you carry genetic echoes of those ancient survivors, the molecular memory of creatures that refused to surrender even when the world itself seemed to be ending. That refusal, that quiet persistence in the face of impossible odds, is part of what makes you possible. The great dying was life's darkest hour, but it was also the night before its brightest dawn. And you, settling into sleep tonight on a world full of flowers and birds and mammals, are part of the magnificent complexity that emerged from that ancient darkness. The fever broke, life endured, and from the ashes of the Permian world, wonders beyond imagination began to grow. Now let's journey forward through deep time to visit perhaps the most famous catastrophe in Earth's history, though not necessarily the most devastating. We're traveling to the end of the Cretaceous period, 66 million years ago, to witness the final day of an empire that had ruled the Earth for 165 million years. This is the story of how the age of dinosaurs ended not with a whimper, but with the most spectacular bang our planet has ever experienced. If you could somehow step into the world of the late Cretaceous, you would find yourself in a place of almost overwhelming abundance and beauty. This was Earth at perhaps its most generous, a greenhouse world where life had grown large and magnificent beyond our modern imagination. The climate was so warm that palm trees grew in Alaska, and crocodiles basked on the shores of an Arctic Ocean that never knew ice. Picture vast forests of conifers and cycads, their canopies towering hundreds of feet above ground, carpeted with ferns that grew as tall as modern trees. Walking through these cathedral-like spaces, you might encounter a Tyrannosaurus rex, but not the monster of popular imagination. This T. Rex moves with surprising grace through dappled sunlight, its massive head swaying gently as it navigates between tree trunks, more like a giant bird than the lumbering beast of old movies. And indeed, it was more bird than we ever realized. Those powerful legs that carried 7 tons of predator across the landscape moved with a rhythm that echoed in the wings of the countless smaller dinosaurs that flitted through the understory. Triceratops moved in herds across flowering meadows, their elaborate frilled heads catching morning light like living art installations. Hadrosaurs filled the air with songs more complex than whale music, their hollow crests resonating with haunting melodies that had echoed across the continents for millions of years. But perhaps most remarkable of all were the flowers. The Cretaceous world was Earth's first experiment with blooming plants, and the results were spectacular. Magnolias the size of dinner plates perfumed the air with fragrances that had never existed before. Early roses, water lilies, and sycamores were revolutionizing the relationship between plants and animals, creating partnerships based on beauty, nectar, and mutual benefit rather than the simple strategies of wind and water dispersal that had dominated plant reproduction for hundreds of millions of years. The oceans of the Cretaceous were warm and shallow, more like vast tropical lagoons than the deep, cold seas we know today. In these waters, ammonites swam with shells coiled in mathematical spirals of perfect beauty, some no larger than coins, others with shells 6 feet across. These weren't just simple mollusks, but sophisticated predators with complex eyes and jet propulsion systems, navigating through underwater forests of kelp and seagrass. Swimming among them were marine reptiles that challenged every assumption about what life in the ocean could become. Mosasaurs, some reaching lengths of 50 feet or more, ruled these ancient seas like dragons. Plesiosaurs, with necks longer than their bodies, moved through the water with 4 paddle-like limbs, while others, the short-necked pliosaurs, were built like submarine missiles designed for high-speed pursuit of prey. Above the surface, pterosaurs owned the skies in ways that seem almost impossible today. Quetzalcoatlus, with wings spanning 35 feet, soared on thermals like living aircraft, while smaller species filled every aerial niche from tiny insectivores to fish-eating specialists that dove into the warm seas with precision that would make a modern pelican jealous. This was a world in full flower, a planet where life had achieved a complexity and grandeur that represented the culmination of nearly 200 million years of Mesozoic evolution. If evolution were a symphony, the late Cretaceous was its most magnificent movement, with every instrument playing in harmony, every theme developed to its fullest expression. But symphonies must end, and this one was about to conclude with a crescendo that would silence the music for millions of years. On what we might call the last normal day in the age of dinosaurs, something was approaching Earth from the outer reaches of our solar system. It was an asteroid, a fragment of rock and metal, about 6 miles in diameter, roughly the size of a major city. For millions of years, it had been traveling through the cold emptiness of space, following an orbital path that would eventually intersect with Earth's journey around the Sun. Picture this cosmic projectile, if you can. It was moving at approximately 45,000 miles per hour, carrying the kinetic energy of billions of nuclear weapons. To put this in perspective, imagine taking the entire city of Los Angeles, accelerating it to 20 times the speed of a bullet, and firing it at the Earth. The numbers are so large they become almost meaningless. But the reality was about to become very meaningful indeed. The asteroid probably approached from the southeast, a brilliant point of light growing brighter and larger in the late afternoon sky over what is now the Yucatan Peninsula of Mexico. For the last few seconds of its journey, it would have been visible as a second sun, blazing across the heavens with a light brighter than anything that had ever illuminated the Earth. The moment of impact lasted perhaps a tenth of a second. In that brief instant, 6 miles of solid rock traveling at cosmic velocity struck the Earth with a force that defies comprehension. The energy released was equivalent to the explosion of 10 billion atomic bombs. The temperature at the point of impact reached tens of thousands of degrees, hot enough to vaporize rock instantly. The asteroid itself ceased to exist in any recognizable form, transformed in an eye blink from solid matter into an expanding sphere of superheated plasma. The ground beneath it, layers of limestone and granite that had taken millions of years to form, simply vanished, leaving behind a crater nearly 100 miles across and 12 miles deep. But this was only the beginning. The impact sent shockwaves through the solid Earth that registered as magnitude 10 or 11 earthquakes, far beyond anything on our modern scales. These seismic waves traveled around the planet several times, triggering volcanic eruptions, landslides, and tsunamis on the opposite side of the world. More devastating still was what happened to the vaporized rock and debris. Millions of tons of molten material were hurled into space, some achieving escape velocity and leaving Earth forever, but most falling back as a blanket of glowing particles that heated the entire atmosphere to oven-like temperatures. For several hours after the impact, the sky literally rained fire as droplets of molten rock fell like burning snow across much of North America. Any dinosaur that looked up at this celestial fireworks display would have been killed instantly, their retinas burned out by radiation more intense than staring directly into the sun. Forests ignited spontaneously under the hellish heat. The air itself became deadly, filled with superheated particles that turned every breath into searing agony. But even this was merely the overture to the true catastrophe that was about to unfold. As the hours passed and the immediate fires died down, vast quantities of dust, soot, and debris began to settle in the upper atmosphere, forming a shroud that would block out the sun for months to come. Imagine the sky gradually darkening, not like an eclipse that lasts for minutes, but like a sunset that never ends. Day by day, week by week, less and less sunlight penetrated the growing veil of particles in the atmosphere. Plants that had never known anything but abundant sunshine began to wither and die. Without photosynthesis, the very foundation of every food web on Earth began to crumble. The world entered what scientists call an impact winter, a period of cold and darkness that lasted far longer than any ordinary winter. Temperatures plummeted as the sun's energy was blocked by the atmospheric debris. In some regions, snow fell in July for the first time in millions of years. For herbivorous dinosaurs, this was a death sentence. The giant sauropods that had fed on tons of vegetation each day found themselves in a world where plants were dying faster than they could regrow. Triceratops and hadrosaurs, adapted for processing vast quantities of low-nutrition plant matter, simply couldn't find enough food to sustain their massive bodies. As the herbivores died, the carnivores followed. A Tyrannosaurus rex needed to eat hundreds of pounds of meat each week, but in a world where the herbivores were starving, such feasts became impossible. The great predators, apex species that had ruled terrestrial ecosystems for tens of millions of years, found themselves reduced to scavenging the carcasses of their former prey. The silence that descended on Earth after the impact was perhaps the most profound change of all. For 165 million years, the world had resonated with dinosaur voices, the low-frequency calls of sauropods that could travel for miles, the complex songs of hadrosaurs, the roars and hisses of predators, the rustling of millions of feet through ancient forests. All of this fell quiet in the space of just a few months. But not everything died. In burrows and caves, in the depths of lakes and rivers, in the spaces between tree roots and under fallen logs, smaller forms of life waited out the darkness. These were creatures that didn't need vast quantities of food, that could survive on seeds and nuts hoarded before the disaster, or on the detritus of the catastrophe itself. Small mammals, most no larger than modern shrews and opossums, huddled in whatever shelter they could find. Their warm-blooded metabolism, which allowed them to regulate their body temperature independently of the environment, became an unexpected advantage in the cooling world. Their ability to digest a wide variety of foods, from insects to seeds to carrion, meant they could make the most of whatever scarce resources remained. Crocodiles and turtles, those ancient survivors whose lineages stretched back to the Triassic, endured, as they had endured so many catastrophes before. Their ability to slow their metabolism, to go months without food, to survive in both water and on land, proved invaluable in the post-impact world. They were living links to the Mesozoic, carrying the memory of the age of reptiles into the new world that was about to emerge. Some dinosaurs survived too, though we don't usually think of them as dinosaurs. Birds, those feathered descendants of theropod dinosaurs, found that their ability to fly gave them access to food sources unavailable to their ground-bound relatives. They could travel vast distances in search of seeds and carrion, could nest in protected places, could adapt their diets more quickly than the specialized giants that were disappearing around them. In the darkness of the impact winter, these survivors couldn't have known that they were inheriting the Earth. They were simply trying to live through each day, finding whatever food they could, staying warm, avoiding predators in a world where the rules of survival had suddenly changed completely. But they were writing the opening chapters of a new evolutionary story. Those tiny mammals carried within their genes the potential for every mammal that would ever exist. The early primates that would eventually give rise to us were already present in embryonic form in the DNA of small creatures, weathering the asteroid winter in primitive burrows. When the skies finally cleared and the sun shone again on a transformed Earth, the survivors found themselves in a world of incredible opportunity. Ecological niches that had been occupied by dinosaurs for over 150 million years were suddenly empty, waiting to be filled by whatever life forms could adapt to exploit them. The evolutionary explosion that followed the extinction was magnificent to contemplate. Within just a few million years, mammals that had spent the entire Mesozoic era as small nocturnal creatures diversified into forms that filled every role the dinosaurs had left vacant. Some became giants themselves, like the massive Uintatherium with its bizarre horned skull. Others took to the air, becoming the first bats. Still others returned to the sea, beginning the evolutionary journey that would eventually produce whales. The birds, those living dinosaurs, exploded into an incredible diversity of forms. Without pterosaurs competing for aerial niches, birds could explore every possible way of living in the sky. Some became giants like the flightless terror birds that ruled early Cenozoic landscapes. Others became tiny jewels like hummingbirds, or master fishermen like pelicans, or nocturnal hunters like owls. Even the surviving reptiles found new opportunities. Snakes, which had appeared during the Cretaceous, diversified rapidly in the post-extinction world. Lizards colonized niches that had never existed before. Crocodiles, freed from competition with large marine reptiles, briefly experimented with life on land, producing species that galloped on long legs like mammalian predators. But perhaps most remarkable of all was what happened to plants. The flowering plants that had been the new innovation of the Cretaceous world suddenly found themselves with greatly reduced competition from conifers and cycads. They began to evolve relationships with insects and birds and mammals that would transform the very appearance of Earth's landscapes. The catastrophe that ended the Cretaceous was indeed the end of an empire, but it was also the beginning of the world we know today. Every oak tree, every rose, every mammal from mouse to whale owes its existence to the ecological opportunity created by that cosmic collision 66 million years ago. As you settle into sleep tonight, you might consider the remarkable chain of events that connects that ancient catastrophe to your own existence. The mammals that survived the impact winter were your ancestors, carrying forward the genetic heritage that would eventually produce consciousness capable of contemplating its own origins. The darkness that followed the asteroid impact was not the end of the story, but the beginning of a new chapter, one that would eventually include cities and music and art, and the gentle voice that speaks to you now across the vastness of deep time. The end of the dinosaur empire was tragic beyond measure, but it was also the necessary prelude to everything that makes your life possible. In the fossil record, the boundary between the Cretaceous and Paleogene periods appears as a thin line of clay enriched with iridium, that rare element more common in asteroids than on Earth. This line, found in rocks around the world, marks the moment when one world ended and another began. Above it, no more dinosaur fossils. Below it, no mammals larger than small dogs. But if you could somehow read that boundary layer with perfect understanding, you would see that it tells a story not of ending, but of beginning, not of death, but of transformation, not of loss, but of the magnificent resilience of life itself. The meteor that ended the age of dinosaurs also began the age of mammals, the age of flowers, the age of consciousness contemplating its own cosmic origins. That transformation continues even now, as you drift towards sleep in a world still being shaped by the consequences of that ancient impact, still unfolding possibilities that were planted in the darkness of that long-ago winter when the survivors waited for the light to return. Now we journey further back than we've ever traveled before, to a time so ancient that it predates not just dinosaurs and flowers and fish, but multicellular life itself. We're going to visit Earth 2.4 billion years ago, during what scientists call the Great Oxidation Event, though perhaps it would be more honest to call it the Great Poisoning. This is the story of how life invented something so toxic that it nearly destroyed itself, and how that near destruction became the foundation for everything complex and beautiful that would follow. If you could somehow find yourself standing on the shores of the Archean Earth, you would die within seconds, not from predators or extreme temperatures, but simply from trying to breathe. The atmosphere contained virtually no free oxygen, that life-giving gas that makes up 21% of every breath you take tonight. Instead, the air was thick with methane, hydrogen sulfide, and carbon dioxide, a cocktail that would be instantly lethal to any oxygen-breathing creature. But you wouldn't just suffocate, you would be struck by the alien beauty of this ancient world. The oceans weren't blue as we know them, but likely purple or green, coloured by populations of bacteria that harvested sunlight using different chemistry than anything alive today. Some used sulfur compounds to capture solar energy, painting the seas in shades of yellow and orange. Others relied on iron, creating waters that shimmered with metallic hues like liquid copper. The sky itself would have appeared different, perhaps with a rusty orange tint from all the iron-rich dust in the atmosphere, and with no protective ozone layer to filter the sun's radiation. Lightning storms would have been more frequent and more violent, crackling through an atmosphere dense with hydrogen and methane. At night, the aurora would have danced closer to the ground, painting the sky in colours that no human eyes have ever seen. This was a world powered by fundamentally different chemistry than our own. Life had existed for over 1 billion years already, but it was life as we can barely imagine it. Vast mats of bacteria covered the seafloor and floated in the water column, some of them building layered structures called stromatolites that rose from the ocean floor like alien cities. These bacterial communities were incredibly sophisticated, with different species working together in partnerships that had already endured for hundreds of millions of years. There were methanogenic bacteria that breathed carbon dioxide and exhaled methane. There were sulfur-reducing bacteria that thrived in waters that would dissolve human skin. There were iron-breathing bacteria that metabolized metal the way we metabolize sugar. This anaerobic world was not a failed experiment or a primitive prototype. It was a fully realized biosphere, as complex and interconnected in its own way as any ecosystem that has existed since. But within this alien paradise, something was stirring that would change everything. Among the countless varieties of bacteria floating in those ancient purple seas, some had stumbled upon a new way of harvesting energy from sunlight. These were the cyanobacteria, and they were about to inadvertently commit the greatest act of environmental terrorism in Earth's history. The innovation that cyanobacteria discovered was photosynthesis, the ability to use sunlight to split water molecules and harvest their energy, releasing oxygen as a waste product. To understand how revolutionary this was, imagine if you could power your car by drinking water and exhaling rocket fuel. Photosynthesis was an incredibly efficient way of capturing solar energy, so much so that cyanobacteria began to outcompete other forms of life wherever sufficient sunlight was available. At first, the oxygen they produced was quickly absorbed by the chemistry of the ancient Earth. Iron dissolved in the oceans would immediately rust when it encountered oxygen, pulling the gas out of the water before it could accumulate. Hydrogen in the atmosphere would combine with oxygen to form water vapor. The Earth itself was hungry for oxygen, having been deprived of it for the first 2 billion years of its existence. But the cyanobacteria kept reproducing, kept photosynthesizing, kept exhaling their poisonous waste into an environment that had never known such chemistry. It's difficult for us to imagine oxygen as a poison, but that's exactly what it was to the anaerobic life forms that had ruled Earth for so long. Oxygen is a highly reactive gas, eager to combine with other molecules in ways that can tear apart the delicate chemistry of life. It can cause what we now call oxidative stress, breaking down proteins and damaging DNA. To the bacteria that had evolved in oxygen-free environments, the accumulation of this gas was like a slow acid bath. Imagine if the plants around your home suddenly started producing chlorine gas instead of oxygen. Imagine if every breath became a little more toxic, every day a little more difficult to survive. This is what was happening to the anaerobic life forms as oxygen levels slowly, inexorably began to rise. The process took hundreds of millions of years, longer than the entire span of complex life on Earth. Century by century, millennium by millennium, the purple seas gradually began to change color as oxygen-producing cyanobacteria spread across the planet. The chemistry of the oceans shifted as iron that had been dissolved in the water began to rust and fall to the seafloor in great red cascades. These falling iron particles created some of the most beautiful geological formations our planet has ever produced. Banded iron formations, as geologists call them, are striped layers of red and black rock that record the slow oxidation of Earth's ancient oceans. Each band represents periods when oxygen levels rose enough to precipitate iron, alternating with periods when the supply of dissolved iron was temporarily exhausted. These formations are like the graveyards of the Archean world, monuments to the chemistry that sustained life for over 1 billion years before oxygen changed everything. The atmosphere itself began to transform, gradually shifting from the methane-rich cocktail of early Earth to something approaching the oxygen-rich mixture we know today. But this transition was catastrophic for most existing life. Methane, which had been a major component of the atmosphere, began to react with the rising oxygen, forming carbon dioxide and water. This changed the very temperature of the planet, as methane is a much more powerful greenhouse gas than carbon dioxide. The Earth cooled dramatically as its methane blanket was stripped away by oxygen. Ice sheets spread from the poles toward the equator in what may have been the most severe ice age in our planet's history. Some scientists believe that the entire Earth became frozen during this period, a snowball Earth, where ice covered the oceans from pole to pole. If this is true, then oxygen didn't just poison most of early life, it froze the planet solid. But life, as it always does, found a way. Among the countless billions of bacteria dying in the rising tide of oxygen, some began to experiment with new forms of metabolism. Instead of being poisoned by oxygen, they learned to use it. They developed chemical pathways that could harness oxygen's destructive power and turn it into an incredibly efficient source of energy. This innovation, which we call aerobic respiration, was like learning to burn rocket fuel safely in a controlled engine, instead of being consumed by its explosive power. Bacteria that could breathe oxygen could extract far more energy from their food than any anaerobic organism had ever managed. A single sugar molecule could yield 38 units of energy through aerobic respiration, compared to just 2 units through the anaerobic processes that had sustained life for billions of years. The bacteria that mastered this new chemistry didn't just survive the oxygen catastrophe they inherited the Earth. As oxygen levels stabilized at higher concentrations, these aerobic organisms found themselves in a world where they could achieve feats of metabolism impossible in the anaerobic past. They could grow larger, move faster, and engage in more complex behaviors than any life form before them. More importantly, some of these oxygen-breathing bacteria began to form partnerships with other cells, eventually leading to the evolution of complex cells with internal structures and nuclei. These eukaryotic cells were the ancestors of every plant, animal, and fungus that has ever existed. In a very real sense, every breath you take connects you to those ancient bacteria that first learned to make peace with poison. The oxygen catastrophe raises profound questions that touch the very heart of how we understand life and evolution. Was this near extinction necessary for consciousness to evolve? Could complex life have emerged through some other pathway that didn't require the near-total destruction of early biospheres? Would a world that remained forever anaerobic have eventually produced its own forms of complexity and beauty? We can't know the answers to these questions, but we can marvel at the strange path that led from that ancient catastrophe to your presence here tonight. The oxygen you breathe was once a poison that killed most life on Earth. The iron in your blood was once dissolved in purple seas, waiting to rust in the first encounters with cyanobacterial waste. The very cells that make up your body are descended from bacteria that learned to survive the end of one world and create another. There's something deeply humbling about this story. It reminds us that even the most fundamental aspects of our existence, the air we breathe, the chemistry that powers our cells, are not permanent features of the universe, but contingent outcomes of evolutionary history. The Great Oxidation Event shows us that life doesn't just adapt to its environment, it transforms that environment so completely that only entirely new forms of life can survive. But there's also something profoundly hopeful in this ancient tale of catastrophe and recovery. The bacteria that survived the oxygen crisis didn't just endure, they used the very force that had threatened to destroy them to build forms of life more complex and beautiful than anything that had existed before. They turned catastrophe into opportunity, poison into power, ending into beginning. As you settle deeper into comfort tonight, breathing easily in an atmosphere that would have been instantly lethal to most early life, you're participating in a process that began 2.4 billion years ago, with the first cyanobacteria learning to split water with sunlight. Every oxygen molecule entering your lungs is a descendant of that ancient waste product that nearly ended life on Earth. The Great Oxidation Event reminds us that mass extinctions aren't just destructive forces, they're also creative ones. By clearing away established forms of life, they make space for innovations that would have been impossible under the old regime. The anaerobic world was beautiful and complex in its own way, but it could never have produced redwood forests or blue whales or human consciousness. Those marvels required the high-energy chemistry that only became possible after life learned to breathe poison. In the banded iron formations that still exist today, we can read the slow rhythm of that ancient transformation. Each stripe tells of rising and falling oxygen levels, of bacterial communities dying and adapting, of chemistry slowly shifting toward the mixture that would eventually sustain consciousness. These rocks are more than geological curiosities. They're the written record of life's first great reinvention of itself. The purple seas are gone forever, and the bacteria that ruled the anaerobic Earth survive now, only in extreme environments where oxygen cannot reach. But their legacy lives on in every cell of your body, in the fundamental chemistry that powers your thoughts and dreams. The oxygen catastrophe was indeed a catastrophe, but it was also the foundation upon which every subsequent chapter of life's story has been built. Tonight, as you drift toward sleep, you might consider the cosmic irony that the very gas sustaining your life was once the agent of the most widespread extinction in Earth's history. And you might wonder what other apparent catastrophes in our planet's past were actually disguised preparations for beauty and complexity we can't yet imagine. The Great Oxidation Event teaches us that sometimes life must nearly destroy itself to discover what it's truly capable of becoming. In the space between ending and beginning, in the chemical crucible of transformation, the seeds of consciousness were planted in poison that learned to bloom. Between the great catastrophes we've explored lie three smaller apocalypses, events that would have been the most devastating disasters imaginable if they had occurred in isolation, but which seem almost gentle compared to the Great Dying or the oxygen catastrophe. Yet each of these smaller extinctions tells its own remarkable story of how life faces challenges, adapts, and emerges transformed. They remind us that catastrophe comes in many forms, sometimes as cosmic impacts or volcanic fury, but just as often as slow changes in climate, ocean chemistry, or the very success of life itself. Let's begin our journey through these three events 445 million years ago, during what geologists call the Ordovician-Silurian extinction. This was Earth during its adolescence, a world finally learning to support complex life, but still finding its balance. If you could visit the Ordovician oceans, you would find yourself in waters more alive than anything we can imagine today, teeming with creatures so strange and wonderful that they seem like the products of some cosmic imagination let loose to play. This was the age of the great marine invertebrates, when the oceans belonged to animals with shells and spines and tentacles but no backbones. Trilobites, those ancient arthropods that had already survived for over 100 million years, had reached peaks of diversity and sophistication that would never be equaled. Some had developed enormous compound eyes with hundreds of individual lenses, capable of detecting polarized light and seeing underwater with clarity that rivals modern optics. Others had evolved elaborate spines and horns that made them look like living Gothic cathedrals. Swimming among the trilobites were nautiloids, relatives of today's chambered nautilus, but grown to magnificent proportions. Some of these ancient cephalopods reached lengths of 20 feet or more, with straight shells like organic spears and tentacles that could crush prey or delicately manipulate the environment with equal skill. They were the sharks of their time, swift and intelligent predators that ruled the Ordovician seas with tentacles and beaks. The seafloor itself was carpeted with gardens of marine life unlike anything that exists today. Crinoids, those lily-like relatives of starfish, swayed in underwater meadows that stretched to every horizon. Bryozoans built delicate colonial structures that looked like underwater lacework. Brachiopods, with their distinctive lampshell shapes, filtered the nutrient-rich waters in numbers that would make modern shellfish populations look sparse by comparison. But perhaps most remarkable of all were the reefs. Not the coral reefs we know today, those hadn't been invented yet, but reef systems built by creatures called tabulate and rugose corals, along with strange sponge-like organisms that could construct massive underwater mountain ranges. These ancient reefs were architectural marvels, some reaching heights that towered hundreds of feet above the surrounding seafloor. Life on land was still in its experimental phase. The first simple plants had begun to colonize the margins of continents, creating patchy green carpets along shorelines and riverbanks. But there were no forests yet, no flowers, no animals larger than primitive arthropods scuttling through the primitive soil. The terrestrial world was still waiting for its great moment. Then the ice began to form, not gradually, as in a normal climate cycle, but rapidly and catastrophically. Within just a few 100,000 years, massive ice sheets spread from the South Pole across much of what is now Africa and South America, which at that time were positioned near the Antarctic region. These weren't ordinary glaciers, but continental ice sheets thousands of feet thick, locking up so much water that global sea levels dropped by over 150 feet. For marine life adapted to shallow, warm seas, this was catastrophic. Entire continental shelves that had been underwater paradises became dry land. Reef systems that had taken millions of years to develop found themselves stranded high and dry, their builders suffocating in the alien environment of air and sunlight. The drop in sea level meant that the remaining ocean basins became smaller and more isolated, breaking up the vast interconnected marine ecosystems that had supported such incredible diversity. But this was only the first punch of a devastating 1-2 combination. After several 100,000 years of glaciation, the ice sheets began to melt as rapidly as they had formed. Sea levels rose again, but now the returning waters were different, colder, with altered chemistry and circulation patterns. Many of the creatures that had managed to survive the initial cooling and sea level drop found themselves facing an equally challenging warming phase. The marine life caught between these extremes faced an impossible situation. Those adapted to cold water were killed by the returning warmth, while those that had evolved to handle the cooling were unprepared for the rapid return of higher temperatures. Approximately 85% of marine species vanished during this climatic whiplash, making it one of the most severe extinction events in Earth's history. Yet from this devastation emerged some of the most important innovations in life's history. The creatures that survived the Ordovician-Silurian extinction included the ancestors of fish, those first vertebrates that would eventually give rise to everything from sharks to humans. In the empty oceans left behind by the extinction, these early fish found unprecedented opportunities to diversify and evolve. The age of vertebrates was about to begin, built on the foundation of one of life's darkest hours. Moving forward through time, we encounter another form of catastrophe entirely during the late Devonian extinction, about 375 million years ago. This disaster was caused not by ice or volcanoes or cosmic impacts, but by one of life's greatest successes, the evolution of forests. The Devonian period was when plants finally learned to reach for the sky. The first true forests spread across the continents, dominated by primitive trees with names like Archaeopteris and Lepidodendron. These weren't forests as we know them today. There were no flowers, no fruits, no bird songs echoing through the canopy, but they were the first ecosystems where life had learned to build vertically, creating three-dimensional habitats that captured sunlight at multiple levels. The success of these early forests created an unexpected problem. As trees grew and died and fell, they released enormous quantities of nutrients into the rivers and streams that drained the continents. Nitrogen and phosphorus, essential elements for life, began flooding into the oceans in concentrations far higher than marine ecosystems had ever experienced. At first, this nutrient bonanza seemed like a gift to marine life. Algae and cyanobacteria bloomed in massive quantities, turning vast stretches of ocean green with photosynthetic life. But this abundance came with a hidden cost. When these enormous algal blooms died and began to decompose, they consumed oxygen from the water faster than it could be replenished. Dead zones began to spread through the oceans like underwater deserts, regions where oxygen levels dropped so low that complex life simply couldn't survive. Fish, trilobites, and other marine animals found themselves trapped between the proliferating life at the surface and the spreading death below. Many species were driven extinct not by too little life, but by too much of it in the wrong places. The irony was profound. The colonization of land by plants, one of the most important developments in Earth's history, nearly killed the ocean ecosystems that had nurtured life for billions of years. It was as if life's success in one realm threatened its existence in another, a reminder that even positive changes can have devastating unintended consequences. But once again, catastrophe became opportunity. The extinction cleared ecological space for new forms of marine life, better adapted to the changed ocean chemistry. More importantly, it accelerated the evolution of terrestrial ecosystems. As marine productivity declined, life on land faced pressure to become more self-sufficient, leading to innovations in plant reproduction, animal locomotion, and the complex food webs that would eventually support dinosaurs and mammals. Our final, smaller apocalypse brings us to 201 million years ago, to the Triassic-Jurassic extinction that ended the Triassic period and opened the door to the age of dinosaurs. This extinction was caused by volcanism again, but volcanism of a very specific and remarkable kind. As the supercontinent Pangaea began to break apart, massive volcanic eruptions along what would become the Atlantic Ocean created what geologists call the Central Atlantic Magmatic Province. Like the Siberian traps before it, this was volcanism on a continental scale, but with its own unique character and consequences. The eruptions lasted for about 600 years, releasing enormous quantities of carbon dioxide, sulfur compounds, and toxic gases into the atmosphere. But perhaps more importantly, they marked the beginning of a new geological era. The volcanic activity was directly related to the rifting that would eventually separate North America from Europe and Africa, creating the Atlantic Ocean and fundamentally reshaping the geography of our planet. For life, this transition was both catastrophic and liberating. The extinction eliminated many of the large archosaurs and mammal-like reptiles that had dominated Triassic ecosystems. Conodonts, those tiny eel-like creatures that had been among the most successful vertebrates for hundreds of millions of years, finally disappeared completely. Many marine reptiles vanished, along with a significant percentage of marine invertebrates. But the groups that survived found themselves inheriting a world with unprecedented opportunities. Dinosaurs, which had been present but relatively uncommon during the Triassic, suddenly found vast ecological niches opening up before them. In the absence of their larger competitors, they began the evolutionary radiation that would make them the dominant land animals for the next 135 million years. Early mammals, still small and mostly nocturnal, also survived the extinction and began their own slow diversification. Crocodiles, those eternal survivors, adapted to the changing world and established lineages that persist virtually unchanged to this day. In the oceans, new groups of marine reptiles evolved to fill the niches left vacant by the extinction. What's remarkable about these three smaller extinctions is how they illustrate the many different ways that life can face existential challenges. The Ordovician-Silurian extinction shows us how climate change can create impossible conditions even for well-adapted life forms. The late Devonian extinction demonstrates how success in one part of the biosphere can threaten life elsewhere. The Triassic-Jurassic extinction reveals how geological forces can simultaneously destroy and create, ending one world while beginning another. Together, these events remind us that extinction is not just about dramatic catastrophes like asteroid impacts or supervolcanic eruptions. It's also about the subtler ways that changing conditions can make survival impossible for even the most successful life forms. They show us that adaptation has limits, that even creatures perfectly suited to their environments can be undone by changes too rapid or too extreme for evolution to accommodate. Yet they also demonstrate life's remarkable ability to find opportunity in catastrophe. Each of these extinctions cleared space for evolutionary innovations that might never have occurred in a more stable world. The Ordovician-Silurian extinction made possible the age of fish. The late Devonian extinction accelerated the development of terrestrial ecosystems. The Triassic-Jurassic extinction enabled the rise of dinosaurs. As you rest tonight, consider how these smaller apocalypses shape the world you inhabit. The oxygen you breathe was influenced by the first forests that caused the late Devonian extinction. The vertebrate body plan that includes your own spine traces back to fish that survived the Ordovician ice ages. The flowering plants that brighten your world evolved in ecosystems shaped by the Triassic-Jurassic transition. These extinctions remind us that catastrophe and creativity are often partners in the dance of evolution. They show us that even smaller disasters can fundamentally reshape the trajectory of life on Earth, and that survival often depends not on being the strongest or most complex, but on being adaptable enough to find opportunity in the ruins of the old world. The pattern of volcanic winters and recovery, of climate swings and ecosystem collapse, and of successful life forms inadvertently creating the conditions for their own extinction. These themes repeat throughout Earth's history, with variations as endless as they are instructive. They remind us that change, even catastrophic change, is not the enemy of life, but one of its most reliable partners in the ongoing creation of beauty, complexity, and wonder. And now we arrive at the most unusual chapter in the story of mass extinctions, the one that is unfolding around us even as you listen to these words. We are living through what many scientists believe to be Earth's sixth great extinction event, but this one is unlike any that came before. For the first time in our planet's 4 billion-year history, a single species has become aware of its own role in reshaping the biosphere. For the first time, consciousness itself has become a geological force. This realization might feel overwhelming, but tonight, as you settle into comfort, I want to explore this moment not with despair, but with wonder. We are witnessing something unprecedented in the universe as we know it. A species becoming aware of its own impact and beginning to grapple with the responsibility that awareness brings. We are living through the first extinction event that might be consciously guided toward a different outcome. The numbers that define our current moment are staggering when placed against the backdrop of deep time. Species are disappearing at rates that are anywhere from 100 to 1,000 times faster than the background extinction rate that has persisted for millions of years. Every day, we lose species that took millions of years to evolve, creatures whose genetic libraries contain solutions to problems we haven't even learned to ask yet. But unlike the volcanic winters and asteroid impacts and ice ages that drove previous extinctions, this one is being caused by success. Human civilization represents one of evolution's most remarkable experiments, a species that learned to manipulate its environment so thoroughly that it could spread to every continent, every climate, every ecological niche on Earth. We have become what ecologists call a super generalist, capable of thriving in conditions that would be impossible for our ancestors. Our success has reshaped the planet in ways both obvious and subtle. We have cleared forests that took millennia to mature, drained wetlands that served as nurseries for countless species, and altered the chemistry of both atmosphere and oceans. We have moved more Earth through mining and construction than all the world's rivers move in a year. We have created entirely new ecosystems, cities and farms and suburbs that favor some forms of life while making survival impossible for others. Yet as we consider this transformation, it's worth remembering that we are not the first species to fundamentally alter Earth's biosphere. The cyanobacteria that caused the Great Oxidation Event changed the planet far more dramatically than humans have managed so far. They transformed the very air and water, creating conditions that killed most existing life. But they also enabled the evolution of complexity and consciousness that eventually led to us. The question that faces us now is whether we can learn to be more intentional about our impact than those ancient bacteria were about theirs. For the first time in Earth's history, a species can look ahead and see the consequences of its actions, can choose to change course before reaching the point of no return. What makes our current moment so remarkable is not just that we're causing an extinction, but that we're aware we're causing it. Every previous mass extinction was driven by unconscious forces, volcanoes that erupted without intent, asteroids that fell without purpose, ice ages that advanced without awareness of their impact. But humans have developed something unprecedented in the history of life: the ability to study our own effects on the biosphere and make conscious choices about what to do with that knowledge. This consciousness brings both tremendous responsibility and unprecedented opportunity. We are the first species that could potentially choose the direction of evolution itself, deciding which lineages survive and which new forms of life we want to encourage. We are the first species that could intentionally preserve the biological heritage of our planet while also creating new forms of beauty and complexity. The speed of change in our current extinction is unlike anything in the geological record. Previous mass extinctions unfolded over thousands or hundreds of thousands of years, giving some species time to adapt to changing conditions. But human-driven changes are happening in decades, sometimes in years. A forest that took centuries to mature can be cleared in weeks. A species that survived ice ages and volcanic winters can be driven extinct by a single infrastructure project. Yet this speed also means that positive changes can happen with unprecedented rapidity. Conservation efforts that would have taken geological ages to show results in the deep past can produce visible improvements within human lifetimes. Species can be brought back from the brink of extinction in decades. Ecosystems can be restored in years. And life, as always, continues to surprise us with its resilience and adaptability. Even as some species disappear, others are evolving in real time to take advantage of the new environments humans have created. Urban environments, which might seem like biological deserts, are actually becoming laboratories for rapid evolution. Peregrine falcons, those magnificent birds of prey, have learned to nest on skyscrapers and hunt pigeons through urban canyons with the same skill their ancestors used to navigate natural cliff faces. Their hunting techniques have evolved to take advantage of the unique geometry of cities, using buildings to create ambush points that would be impossible in natural terrain. Coyotes have expanded their range to include virtually every major city in North America, learning to navigate traffic patterns and hunt in parks and suburban yards. Their social structures have evolved to take advantage of urban food sources, and they've developed new behaviors that would be completely foreign to their purely wild ancestors. Some birds have learned to incorporate human-made materials into their nests with remarkable creativity. Weaver birds in Africa include colorful plastic strips and bits of wire in their elaborate constructions, creating nests that are more durable and weather-resistant than traditional designs. House finches in cities sing at higher frequencies than their rural cousins, adapting their songs to cut through urban noise pollution. Plants, too, are evolving rapidly in response to human environments. Some populations of evening primroses have evolved to bloom earlier, and with different flower shapes to attract urban pollinators. Certain grasses have developed the ability to tolerate road salt concentrations that would kill their ancestors. Tree species in cities are evolving different leaf shapes and root systems to deal with air pollution and compacted soils. But perhaps most remarkable are the conservation success stories that show what becomes possible when human consciousness is directed toward preservation rather than exploitation. The California condor was reduced to just 27 individuals in the 1980s, a population so small that extinction seemed inevitable. Today, through intensive breeding programs and habitat protection, more than 500 condors soar over the American Southwest. Grey whales were hunted nearly to extinction, with populations dropping to perhaps a few hundred individuals. Protected by international treaties and conservation efforts, they have recovered to healthy population levels, with some populations removed from endangered species lists entirely. Humpback whales, whose songs once seemed destined to fall silent forever, now fill the oceans with their complex melodies as their numbers continue to recover. Bald eagles, poisoned nearly to extinction by DDT and habitat loss, now soar over landscapes where they hadn't been seen for decades. Wolves have returned to Yellowstone, not only surviving but fundamentally transforming the ecosystem in ways that ecologists are still discovering. Their presence has changed the behavior of deer and elk, which in turn has allowed forests to regenerate, which has created habitat for countless other species. These recovery stories remind us that extinction is not always forever, at least not in the way we once understood it. We now have technologies that seemed like pure science fiction just decades ago. Genetic rescue techniques can increase diversity in small populations. De-extinction technologies, while still in their infancy, might eventually allow us to restore species that have been lost entirely. But perhaps more importantly, we're learning to design human systems that work with natural processes rather than against them. Cities are beginning to incorporate green corridors that allow wildlife to move through urban environments. Farms are experimenting with practices that support biodiversity while maintaining productivity. Industries are developing technologies that mimic natural processes, creating manufacturing systems that produce no waste and require no toxic inputs. The long view of deep time offers both sobering perspective and genuine hope. Every previous mass extinction was followed by an explosion of evolutionary creativity that produced new forms of life more complex and beautiful than what came before. The Great Dying cleared the way for dinosaurs and mammals. The asteroid impact that ended the Cretaceous enabled the flowering of mammalian diversity that eventually led to consciousness. But this time, consciousness itself is part of the equation. We don't have to wait for evolutionary timescales to see what emerges from our current extinction event. We can participate actively in shaping what comes next. We can choose which species survive, which ecosystems we want to preserve, and which new forms of life we want to encourage. This doesn't mean we can or should try to control evolution entirely. Natural selection and genetic drift, and all the other forces that drive biological change will continue to operate regardless of our intentions. but we can influence the direction of those forces in ways that no species has ever been able to do before. We're already seeing the beginnings of this conscious guidance of evolution. Conservation biologists are using genetic rescue techniques to increase diversity in endangered populations. Restoration ecologists are rebuilding ecosystems, using principles learned from studying how life recovers from natural disasters. Urban planners are designing cities that serve as habitat for both humans and wildlife. Perhaps most remarkably, we're beginning to develop technologies that could allow us to extend our responsibility beyond Earth itself. As we learn to survive in space, we're also learning to create closed-loop life support systems that could serve as seed banks for terrestrial life. The same technologies that might allow humans to live on Mars could also serve as insurance policies for Earth's biodiversity. But the most important technology we're developing may be the simplest: the ability to see ourselves as part of the larger community of life rather than separate from it. Indigenous cultures around the world have maintained this perspective for thousands of years, understanding that human welfare is inseparable from the health of the ecosystems that support us. Modern science is rediscovering this ancient wisdom through new fields like ecosystem services research, which quantifies the economic value of natural processes like pollination, water purification, and carbon sequestration. We're learning that biodiversity isn't just aesthetically valuable but economically essential, that the stability of human civilization depends on maintaining the complex web of relationships that connect all life on Earth. This shift in perspective is perhaps the most hopeful aspect of our current moment. For the first time, large numbers of humans are beginning to understand that we are not separate from nature, but part of it. Not masters of the biosphere, but participants in its ongoing evolution. The extinction we're living through is certainly a tragedy. Every species that disappears takes with it millions of years of evolutionary innovation, genetic information that could have been crucial for adapting to future challenges. The silence that follows the last song of an extinct bird species is a loss that echoes through deep time. But our current extinction is also an opportunity to demonstrate what consciousness can accomplish when it's directed toward preservation and restoration rather than exploitation. We have the chance to show that awareness can be a force for creation as well as destruction, that intelligence can learn to live in harmony with the natural processes that created it. As you settle into sleep tonight, consider that you are living through one of the most important moments in the history of life on Earth. You are part of the first generation of humans to fully understand the scope of our impact on the biosphere, and potentially part of the last generation that will have the opportunity to prevent the worst outcomes of our current trajectory. But you are also part of the first species that has the tools and knowledge necessary to consciously guide the future of evolution itself. The choices being made by humans today will influence the trajectory of life on Earth for millions of years to come. In a very real sense, we have become the authors of the next chapter in life's story. This is both a sobering responsibility and an extraordinary privilege. We are the universe becoming aware of itself, consciousness emerging from the long evolution of matter and energy into forms capable of understanding their own origins and choosing their own destiny. The sixth extinction is our chapter in the great book of life on Earth. How it ends depends on the choices we make in the coming decades, but for the first time in the planet's history, those choices will be made consciously, with full awareness of their consequences, and with the intention of creating a future where both human civilization and wild nature can flourish together. The story is still being written, and you are one of its authors. Rest tonight, knowing that consciousness has arrived at a moment when it can make a difference, when awareness can become the tool that guides life toward greater complexity and beauty, rather than toward simplification and silence. The sixth extinction is not just an ending, it is also a beginning, the first chapter in the age of conscious evolution, when intelligence learned to serve life rather than merely exploit it. And that beginning starts with each choice we make. Each day we choose to see ourselves as part of the community of life rather than separate from it. Tomorrow, the story continues, and consciousness gets another chance to show what it can accomplish when it chooses to be a force for creation rather than destruction, for preservation rather than exploitation, for the flourishing of all life rather than the dominance of just one species. The future remains unwritten, waiting for consciousness to decide what role it wants to play in the next chapter of evolution's greatest experiment. The emergence of mind from matter and the responsibility that comes with the power to choose. As we've journeyed together through the great catastrophes of Earth's past, you might have noticed something remarkable emerging from each story of devastation. Mass extinctions, those moments when life seems to come closest to complete failure, are also the moments when life discovers its greatest capacity for reinvention. Tonight, as you settle into the gentle rhythm of approaching sleep, let's explore this profound paradox. How endings become beginnings, how destruction enables creation, and how the spaces between catastrophes reveal the deepest truths about what it means to be alive on this ancient, resilient planet. There's a temptation, when studying mass extinctions, to see them as unfortunate interruptions in life's steady progress toward greater complexity and beauty. We imagine that without these catastrophic setbacks, evolution might have proceeded smoothly from simple to complex, from primitive to sophisticated, following some predetermined path toward consciousness and civilization. But this view misses something fundamental about how creativity actually works in the natural world. Mass extinctions aren't obstacles to evolution. They are evolution's most powerful engines of innovation. They serve as cosmic reset buttons that clear away established forms of life and create vast expanses of ecological opportunity for whatever survivors remain. They are the spaces between notes that give music its rhythm, the pauses between breaths that make breathing possible, the darkness between dawn and dusk that defines the very concept of day. Consider what happens in the immediate aftermath of a mass extinction. The Earth becomes, in essence, a planet-sized laboratory for evolutionary experimentation. Survivors find themselves in a world where the old rules no longer apply, where niches that had been occupied for millions of years suddenly stand empty, where resources that had been monopolized by dominant species become available to anyone creative enough to exploit them. In this emptied world, natural selection operates with an intensity and freedom impossible under normal circumstances. Small genetic variations that might have been insignificant in a crowded ecosystem can become the foundation for entirely new ways of life. Modest behavioral adaptations can lead to radical ecological innovations. Survivors don't just recover, they explode into forms that would have been impossible in the pre-extinction world. The fossil record tells this story with remarkable consistency. After each of the major mass extinctions, we see what paleontologists call adaptive radiations, periods of rapid evolutionary diversification, when surviving lineages split into multiple species, each exploring different solutions to the challenges of life in a transformed world. These radiations often produce more diversity than existed before the extinction, creating biological communities more complex and interconnected than anything that came before. The mammalian radiation that followed the end Cretaceous extinction is perhaps the most dramatic example we can observe in detail. In the immediate aftermath of the asteroid impact, mammals were small, generalized creatures that had spent over 100 million years living in the shadows of dinosaurs. Most were no larger than modern shrews, with simple teeth adapted for eating insects and small prey, and relatively primitive brains that served their modest ecological roles. But within just 10 million years of the extinction, the blink of an eye, in geological terms, mammals had diversified into an array of forms that defies imagination. Some, like the massive Uintatherium, grew to the size of modern rhinos and developed elaborate horned skulls that made them look like living mythological creatures. Others, like the early horses, began the long evolutionary journey toward running on single toes across open grasslands that didn't yet exist. Perhaps most remarkably, some mammals returned to the sea, beginning the evolutionary odyssey that would eventually produce whales. These early proto-whales still had legs and lived partly on land, but they were already experimenting with the aquatic lifestyle that would lead to the largest animals ever to live on Earth. In the space of a few million years, mammals went from being tiny generalists to filling nearly every conceivable ecological niche on land, in the air, and in the sea. This explosive diversification wasn't just about mammals getting bigger or more numerous. It was about the evolution of entirely new ways of living, new forms of intelligence, new types of social organization, new strategies for finding food, avoiding predators, and reproducing successfully. The post-extinction world became a testing ground for innovations that would have been impossible when dinosaurs dominated terrestrial ecosystems. But mammals weren't the only beneficiaries of the Cretaceous extinction. Birds, those surviving dinosaurs, underwent their own remarkable radiation. Freed from competition with pterosaurs in the air and with large theropod dinosaurs on the ground, birds evolved into forms ranging from tiny hummingbirds that could hover like helicopters to massive flightless predators that ruled early Cenozoic landscapes like feathered tyrannosaurs. Flowering plants, which had appeared during the Cretaceous but remained relatively limited in diversity, suddenly found themselves in a world where their animal pollinators and seed dispersers were evolving rapidly into new forms. The co-evolutionary dance between flowering plants and their animal partners intensified, leading to innovations like the grasses that would eventually create the savannas, where human ancestors learned to walk upright. This pattern of post-extinction innovation repeats throughout the fossil record, with variations as beautiful as they are instructive. After the Permian extinction, the archosaurs that gave rise to dinosaurs and crocodiles began their own adaptive radiation, eventually producing everything from tiny, bird-like dinosaurs to the largest land animals that ever lived. After the Ordovician extinction, the surviving marine invertebrates diversified into forms that would dominate Paleozoic seas for hundreds of millions of years. Each extinction creates its own unique set of opportunities, its own particular configuration of empty niches and available resources. The specific forms that emerge depend on which lineages happen to survive, which genetic variations happen to be present in the surviving populations, and which environmental challenges the post-extinction world presents. There's a profound element of chance in these radiations, a reminder that the history of life is not a predetermined script but an improvisation played out over geological time. This element of contingency means that every species alive today, including us, is incredibly lucky to exist. We are the products of countless survival bottlenecks, each one narrowing the range of possible futures until, by some remarkable combination of adaptation and chance, our particular lineage managed to persist. If any one of the mass extinctions had played out slightly differently, if different species had survived or different mutations had occurred in the aftermath, the entire trajectory of evolution might have led to a completely different world. Consider the chain of improbable events that led to your existence. Your mammalian ancestors survived the Permian extinction when 96% of species perished. They survived the Triassic-Jurassic extinction that eliminated many of their competitors. They survived the Cretaceous impact that ended the age of dinosaurs. At each bottleneck, the lineage that would eventually produce primates, and eventually you, hung on by threads so thin that their survival seems almost miraculous. But it's not just the major mass extinctions that shaped your evolutionary history. Countless smaller catastrophes, regional disasters, climate fluctuations, and ecological disruptions also acted as filters, eliminating some lineages while allowing others to pass through. Each of these events was another roll of the evolutionary dice, another opportunity for the chain of ancestry leading to you to be broken forever. The fact that you exist means that your ancestors were not just lucky, they were lucky again and again and again, across hundreds of millions of years of geological time. Every breath you take is a testament to an unbroken chain of survival, stretching back to the earliest cells that learned to extract energy from their environment and pass their genetic information to the next generation. This perspective transforms how we understand both extinction and survival. Extinction isn't failure, it's the price life pays for the opportunity to experiment with new forms. Most experiments fail, but the ones that succeed can be spectacular beyond imagination. The lineages that survive extinction events aren't necessarily the best in any absolute sense. They're the ones that happen to have the right combination of traits for the specific challenges they face. As we examine the patterns that emerge across different mass extinctions, certain common factors become apparent. Climate change, in various forms, appears in almost every extinction event. Sometimes it's global cooling, as in the Ordovician Ice Age. Sometimes it's global warming, as in the Permian greenhouse crisis. Sometimes it's rapid fluctuations between extremes that make adaptation impossible. Ocean chemistry changes also appear repeatedly in the extinction record. The acidification and oxygen depletion that characterized the Permian extinction echoes in smaller scale during other events. The nutrient pollution that drove the late Devonian extinction shows how even life's successes can create conditions hostile to life's continued prosperity. Volcanic activity appears as a contributing factor in multiple extinctions, not just through the direct effects of lava flows, but through the atmospheric changes caused by massive gas emissions. The Siberian Traps and the Central Atlantic Magmatic Province represent volcanism on scales difficult to comprehend, but even smaller volcanic events can have cascading effects on global climate and ocean chemistry. These patterns suggest that life has certain consistent vulnerabilities that persist across geological time. Complex ecosystems, despite their apparent stability, are surprisingly fragile when faced with rapid environmental change. Food webs that have developed over millions of years can collapse in centuries or decades when their foundations are disrupted. Species that have successfully specialized for particular environmental conditions can become evolutionary dead ends when those conditions change too rapidly for adaptation to keep pace. But the patterns also reveal life's consistent strengths. Small, Generalized organisms tend to survive better than large, specialized ones. Species with wide geographic distributions weather catastrophes better than those with limited ranges. Communities with high diversity tend to be more resilient than simplified ecosystems. Sexual reproduction, despite its costs, provides the genetic variation necessary for adaptation to changed conditions. Perhaps most importantly, the patterns reveal the crucial role of what ecologists call refugia, places where conditions remain stable enough for life to persist during times of global catastrophe. These refugia serve as evolutionary lifeboats, preserving genetic diversity and ecological relationships that can eventually recolonize damaged areas when conditions improve. During the Permian extinction, small pockets of relatively stable environment allowed some lineages to survive the global crisis. High-latitude regions that escaped the worst effects of greenhouse warming, deep ocean basins that retained some oxygen, isolated islands that maintained more stable climates. These refugia served as the seed banks from which post-extinction recovery eventually emerged. The concept of refugia helps us understand how life manages to persist through even the most severe catastrophes. It's not that life survives catastrophe by being individually tough enough to endure impossible conditions. Instead, life survives by being diverse enough and widespread enough that some populations always find places where conditions remain tolerable, even during global crises. This strategy of survival through dispersal and diversity is one of life's most fundamental innovations. By spreading across multiple environments and evolving into multiple forms, life ensures that no single catastrophe can eliminate all of its experiments simultaneously. The price of this insurance policy is high. Most populations and most species will be lost during any major crisis. But the payoff is the preservation of enough genetic and ecological diversity to enable recovery and continued innovation. The timescales of extinction and recovery reveal another important pattern in the fossil record. While mass extinctions can occur in centuries, millennia, or at most hundreds of thousands of years, recovery always takes much longer. Full ecological recovery from a major mass extinction typically requires 5–10 million years, sometimes longer. This asymmetry reflects the fundamental difference between destruction and creation. Tearing down complex systems is always faster than building them up. During the recovery period, ecosystems pass through predictable stages of development. Initially, the post-extinction world is dominated by simple communities of generalist species that can exploit the abundant resources left behind by the catastrophe. These pioneer communities are often characterized by low diversity but high productivity, as the surviving species take advantage of reduced competition and abundant ecological opportunities. Over time, these simple communities gradually become more complex, as surviving lineages diversify and new ecological relationships develop. Predator-prey relationships become more sophisticated, symbiotic partnerships evolve, and food webs develop the intricate interconnections that characterize mature ecosystems. This process of ecological succession occurs not just over centuries or millennia, as in the recovery from smaller disturbances, but over millions of years as evolution creates new forms to fill the niches left empty by extinction. The end point of recovery is not a return to pre-extinction conditions, but the emergence of entirely new types of ecosystems. The post-Permian world of the Triassic looked nothing like the pre-extinction Permian world, despite being built from the genetic heritage of Permian survivors. The Cenozoic world that emerged after the Cretaceous extinction was fundamentally different from the Mesozoic world of dinosaurs, even though it was populated by the descendants of Cretaceous survivors. This pattern suggests that mass extinctions serve as one-way doors in the history of life. They eliminate certain possibilities forever, while opening up new ones that couldn't have existed before. The trilobites that disappeared in the Permian extinction were never replaced by similar forms, even though the niches they occupied were eventually filled by other types of arthropods. The large marine reptiles that vanished at the end of the Cretaceous were never duplicated, even though whales eventually became the ocean's top predators. Each extinction thus represents both an ending and a beginning, a closing of certain evolutionary pathways and an opening of others. The creativity that emerges from destruction is not simply a restoration of what was lost, but an exploration of entirely new possibilities for what life might become. This creative aspect of extinction provides a different lens through which to view our current biodiversity crisis. While the species we lose to human activities are gone forever, the ecological space they leave behind will not remain empty indefinitely. Evolution will eventually fill those niches, though the forms that emerge may be very different from what we're losing today. The question for our current moment is not whether life will recover from the Anthropocene extinction. It will. Given enough time, the question is what forms that recovery will take, and whether humans will be around to witness and participate in it. Previous mass extinctions were followed by radiations that produced new forms of beauty and complexity that surpassed what came before. But those radiations took millions of years to unfold, far longer than human civilization has existed. Our current extinction offers both dangers and opportunities that are unprecedented in the geological record. On one hand, we're causing changes to the biosphere at speeds that may exceed life's ability to adapt. On the other hand, we're the first species with the awareness and technology to potentially guide the recovery process, to consciously preserve the genetic heritage necessary for future radiations, and to create conditions that favor the emergence of new forms of life rather than simply their destruction. The wisdom hidden in the fossil record suggests several principles that might guide our approach to this unprecedented situation. First, diversity is life's most effective insurance policy against catastrophe. Every species that survives our current activities carries genetic information that might be crucial for adapting to future challenges we can't yet imagine. Preserving as much of this diversity as possible preserves options for the future. Second, refugia are crucial for survival through catastrophic periods, protecting large areas of habitat where natural processes can continue relatively undisturbed, provides safe spaces for evolution to continue its experiments. These refugia serve not just as museums of current biodiversity, but as laboratories for future evolution. Third, small populations can carry forward entire evolutionary lineages if they're given sufficient time and space. Many of today's most successful groups descended from tiny populations that survived mass extinctions by finding suitable refugia. This suggests that even our current conservation efforts, which might seem inadequate to prevent widespread extinction, could still preserve the seeds of future evolutionary radiations. Fourth, the interactions between species are as important as the species themselves. Ecosystems are not just collections of individual species but networks of relationships, predator-prey interactions, pollination partnerships, symbiotic collaborations, competitive dynamics. Preserving these relationships preserves the ecological context within which evolution creates new forms of life. The deep time perspective offered by the study of mass extinctions provides both humility and hope. Humility, because it reminds us that we're not the first species to drastically alter the biosphere, and that previous alterations led to catastrophic consequences for the species that caused them. Hope, because it shows us that life has an extraordinary capacity for recovery and innovation, even after catastrophes that seem terminal. Every species alive today descended from survivors of multiple mass extinctions. This means that every organism carries within its genes the molecular memory of catastrophe and recovery, the genetic heritage of lineages that refuse to surrender even when the world itself seemed to be ending. This heritage includes not just the ability to survive under extreme conditions, but the capacity to innovate, to explore new ecological possibilities, to evolve into forms that would have been impossible under pre-catastrophe conditions. As you prepare for sleep tonight, consider that you are part of this ancient tradition of survival and innovation. The cells that make up your body carry genetic sequences that have passed through every major extinction event in Earth's history. You are built from molecular components that have experienced the oxygen catastrophe, the Great Dying, the End Cretaceous impact, and countless smaller disasters. You are, quite literally, made from the same stuff as the survivors who weathered catastrophes that make our current challenges seem modest by comparison. But you're also part of something new in the history of life. The first species with the consciousness to understand its own impact on the biosphere and the potential ability to guide the outcomes of environmental change. The spaces between endings that we're exploring tonight are not just historical curiosities, but active laboratories where the future of life on Earth is being determined by choices being made today. The patterns we see in the fossil record suggest that our current extinction will eventually be followed by recovery and innovation that surpasses what we're losing today. But unlike previous recoveries, this one might be guided by consciousness rather than left entirely to chance. We have the opportunity to influence not just which species survive, but how they evolve. Not just what ecosystems persist, but how they develop. Not just whether life recovers, but what forms that recovery takes. This is both an enormous responsibility and an extraordinary opportunity. We are living in one of the spaces between endings, in the pause between the old world and the new one, in the creative interval where catastrophe becomes opportunity and destruction becomes the foundation for new forms of creation. The fossil record tells us that these spaces are always temporary. Eventually, the creative ferment of post-extinction evolution settles into new patterns of ecological stability that persist for millions of years. But while they last, these spaces between endings are periods of almost unlimited possibility, when evolution experiments with forms and relationships that would never emerge under more stable conditions. We don't know yet what will emerge from our current space between endings, but we know from deep time that whatever emerges will likely be more complex, more beautiful, and more sophisticated than what existed before. Life's creativity, unleashed by catastrophe and guided by the mysterious forces of natural selection, has never failed to produce wonders that exceed our imagination. Tonight, as you drift toward your own daily renewal through sleep, you might consider that you are witness to one of the most creative periods in Earth's history. The spaces between endings are always times of mourning for what is lost, but they are also times of birth for what is yet to be born. And consciousness, for the first time in the planet's history, has arrived at a moment when it can participate in guiding what emerges from the creative chaos of mass extinction. The story is still being written. The space between this ending and the next beginning is still unfolding. And you, carrying within your cells the genetic memory of every survival and every innovation that came before, are part of both the ending and the beginning, part of both the mourning and the creation, part of the ancient rhythm of catastrophe and recovery that has shaped life on Earth for billions of years. Rest tonight knowing that the spaces between endings are not empty voids but pregnant pauses, not final conclusions but eternal renewals, not the absence of life but the workshop where life reinvents itself again and again, always finding new ways to be beautiful, always discovering new forms of complexity, always persisting through whatever catastrophes the universe provides as opportunities for becoming something more than it was before. As our journey through deep time draws toward its gentle conclusion, we arrive at perhaps the most remarkable realization of all. The story we've been exploring together is not ancient history, but living memory. Every breath you take as you settle into sleep tonight connects you directly to that first moment, nearly 4 billion years ago, when simple chemistry learned to become life. The thread that links you to those earliest cells has never been broken, not once, despite every catastrophe we've witnessed together. This is not metaphor or poetry, though it partakes of both. This is literal truth written in the language of molecules and genes. The DNA in your cells carries sequences that are older than any mountain range on Earth, older than any ocean basin, older than the very continents themselves. Some of the genetic instructions that build your body today were first written when the planet was still learning what life could be, and they have been passed down, parent to offspring, through an unbroken chain of survival that spans geological epochs. Consider what this means in the most concrete terms. The cellular machinery that allows you to extract energy from food operates according to principles first established by bacteria living in the Archean seas. The genetic code that translates DNA into proteins is essentially identical in every living thing, from the smallest microbe to the largest whale, because we all inherited it from the same ancient ancestors. The fundamental chemistry of life, the way molecules store and transfer energy, the methods cells use to repair and replicate themselves, the basic mechanisms of growth and reproduction, all of these were perfected billions of years ago and have been preserved across every mass extinction, every climate catastrophe, every cosmic disaster that has befallen our planet. You are not just related to every other living thing, you are made from the same molecular components, built according to the same basic instructions, powered by the same ancient biochemical processes that have sustained life since its earliest emergence. The water in your body has flowed through countless other organisms across deep time. The carbon atoms in your DNA were once part of primordial seas, ancient atmospheres, long extinct creatures whose names we'll never know. The iron in your blood was forged in the nuclear furnaces of dying stars and has cycled through Earth's systems for billions of years, carrying oxygen through the bodies of countless ancestors. This continuity is perhaps life's most remarkable achievement. Despite every catastrophe, despite extinction events that eliminated 90% or more of existing species, the fundamental project of life, the business of turning chemistry into experience, matter into awareness, has never ceased. The particular forms have changed dramatically, repeatedly, beyond recognition, but the underlying process, the basic conversation between genes and environment that we call evolution, has continued uninterrupted for 4 billion years. Every creature alive today, from the bacteria in your stomach to the trees outside your window, is a direct descendant of survivors. Not just survivors of one catastrophe, but survivors of every catastrophe. Each species carries within its genetic heritage the accumulated wisdom of countless generations that refused to surrender when the world seemed to be ending. This is why extinction makes life more precious, not less. Every organism represents not just its own individual existence, but the culmination of an epic survival story that stretches back to the beginning of life itself. The genetic memory of catastrophes is literally written into our DNA, though in ways so subtle we've only recently learned to read them. Molecular biologists studying stress response systems in modern organisms have discovered genes and proteins that show clear signs of having evolved in response to ancient environmental crises. The cellular mechanisms that help you survive illness, injury, or extreme stress are refined versions of systems first developed by your ancestors to survive mass extinctions. Some of the most fundamental aspects of human biology bear the signatures of our catastrophic heritage. Our ability to store fat for lean times, our stress response systems that flood our bodies with hormones during emergencies, our immune systems that can rapidly adapt to new threats. All of these reflect evolutionary solutions to the kinds of challenges that mass extinctions impose. We carry within ourselves the molecular memory of starvation, environmental toxicity, climate extremes, and ecosystem collapse. But we also carry something else: the genetic heritage of every innovation that allowed life to not just survive but flourish after catastrophe. The metabolic pathways that let us extract energy from food are more efficient than anything that existed before the Great Oxidation Event. The nervous systems that generate our thoughts and dreams are more sophisticated than anything possible before complex multicellular life evolved. The social instincts that allow us to cooperate, communicate, and care for one another represent evolutionary advances that emerged over hundreds of millions of years of selection for survival in challenging environments. This perspective transforms how we understand our own existence. We are not accidents or afterthoughts in the story of life. We are the culmination of the longest, most improbable success story in the known universe. Every human being represents the successful completion of a 4 billion year survival course that has eliminated more species than currently exist. You are here not despite the mass extinctions we've explored together, but because of them. The pattern that emerges when we examine the full sweep of evolutionary history is both humbling and inspiring. Each major extinction event was followed, not just by recovery, but by the emergence of life forms more complex, more sophisticated, and more aware than anything that existed before. The Great Oxidation Event, catastrophic as it was for anaerobic life, made possible the evolution of complex cells with internal structures and nuclei. The Permian extinction, devastating as it was, cleared the way for dinosaurs, mammals, and flowering plants. The Cretaceous impact, tragic as it was for dinosaurs, enabled the mammalian radiation that eventually produced consciousness capable of contemplating its own origins. There's a pattern here that suggests something profound about the relationship between catastrophe and creativity in evolutionary processes. Mass extinctions don't just randomly eliminate life forms, they tend to remove species that have become highly specialized for particular environmental conditions, leaving behind generalists that can adapt to changed circumstances. The surviving generalists then diversify rapidly into new specialists adapted for the post-extinction world, often achieving levels of complexity and sophistication that surpass anything that existed before. This process has repeated itself through every major extinction, each time pushing the boundaries of what life can accomplish. The trend is not just toward greater diversity, though that's certainly part of it, but toward greater complexity, greater sophistication, and what we might call greater awareness. Even simple organisms today possess sensory systems, information processing capabilities, and behavioral repertoires that dwarf those of their ancient ancestors. The role of mass death in creating consciousness is one of the most profound puzzles in evolutionary biology. Complex nervous systems, which are the foundation of awareness and intelligence, require enormous amounts of energy to build and maintain. They also take up significant space and represent vulnerability to injury. For most of life's history, the costs of large brains outweighed their benefits. Simple nervous systems were sufficient for survival in established ecosystems, where most niches were already occupied, but mass extinctions changed this calculation dramatically. In the aftermath of catastrophe, when ecosystems are disrupted and new ecological opportunities abound, the ability to process information rapidly, to learn from experience, to adapt behavior to changing conditions, becomes enormously valuable. This is when evolution tends to favor increased intelligence, more sophisticated nervous systems, greater behavioral flexibility, The mammals that survived the end Cretaceous extinction were not the smartest creatures of their time. But in the empty world left behind by the dinosaurs, those with slightly better learning abilities, slightly more flexible behaviors, slightly more sophisticated social structures, gained significant advantages. Over millions of years of post-extinction evolution, these modest advantages compounded into the extraordinary cognitive abilities that characterize modern mammals. Primates, the group that eventually gave rise to humans, represent the culmination of this trend toward increasing intelligence and social sophistication. Our ancestors survived not because they were the strongest or fastest creatures in their environments, but because they were among the most adaptable, most socially cooperative, most capable of learning from experience and passing that learning to their offspring. The development of language, tool use, and culture in human lineages represents something unprecedented in the history of life. The emergence of consciousness capable of understanding its own evolutionary origins. For the first time in 4 billion years of life on Earth, evolution has produced a species that can study its own history, comprehend the forces that shaped it, and potentially influence the direction of future evolutionary change. This emergence of self-aware consciousness may represent the most significant transition in the history of life since the evolution of sexual reproduction or the development of multicellularity. We are not just another species among millions, but the first species capable of understanding the story we've been exploring together tonight. We are evolution becoming aware of itself, life learning to contemplate its own nature and history. This awareness brings both extraordinary privileges and sobering responsibilities. We are the first creatures capable of reading the fossil record and understanding what it tells us about extinction and recovery. We are the first to grasp the deep time perspective that puts our own existence in cosmic context. We are the first to realize that we are part of an ongoing story that began with the first self-replicating molecules and continues today in every choice we make about how to live on this planet. But consciousness also brings the responsibility of choice in ways that no species has ever faced before. Previous extinction events were caused by unconscious forces, volcanic eruptions, climate changes, asteroid impacts that unfolded according to physical laws without regard for their biological consequences. But humans have become a conscious geological force, capable of understanding our impact on the biosphere and potentially capable of choosing different courses of action. This represents a fundamental transition in the nature of evolution itself. For 4 billion years, natural selection operated entirely through unconscious processes. Genetic mutations arose randomly. Environmental pressures selected for survival and reproduction without foresight or intent. Evolutionary innovations emerged through trial and error over millions of years. But consciousness introduces the possibility of intentional evolution, of conscious choice about the direction of biological change. We can already see the beginnings of this transition in conservation biology, genetic engineering, ecological restoration, and the conscious design of sustainable human systems. For the first time in Earth's history, a species is making deliberate choices about which other species survive, which ecosystems persist, which evolutionary experiments continue. We are beginning to take conscious responsibility for the trajectory of life on Earth. This doesn't mean we can control evolution. The forces of genetic variation, natural selection, and environmental change will continue to operate regardless of human intentions. But it does mean that consciousness has become a significant factor in evolutionary processes for the first time in the planet's history. The choices we make about energy systems, land use, conservation priorities, and technological development will influence the direction of evolution for millions of years to come. Our place in deep time is thus both humbling and empowering. Humbling because it reminds us that we are recent arrivals in a story that began long before us and will continue long after us. Empowering because it suggests that consciousness may represent evolution's next great innovation, the development of life forms capable of understanding and potentially guiding the very processes that created them. The possibility that we are part of life's growing self-awareness is perhaps the most hopeful perspective we can take on our current moment. If consciousness represents a general trend in evolution rather than a unique accident, then intelligence and awareness may be more common in the universe than we currently imagine. The development of self-aware life forms may be one of the natural outcomes of evolutionary processes operating over geological timescales. This perspective suggests that our current extinction crisis, traumatic as it is, may also represent the birth pangs of a new phase in evolution. The emergence of conscious life, capable of taking responsibility for the continuation and diversification of the evolutionary process itself. We may be witnessing not just another mass extinction, but the transition from unconscious to conscious evolution, from random to intentional selection, from accidental to purposeful change. The silence preserved in the fossil record teaches us profound lessons about both presence and absence, about the preciousness of life and the inevitability of change. Every fossil represents a moment when some particular form of life was buried quickly enough to preserve its structure for millions or hundreds of millions of years. These are not random samples, but witnesses to moments of catastrophe, volcanic eruptions, floods, mudslides, asteroid impacts that ended individual lives but preserved them for deep time. In this sense, the fossil record is a vast library of endings, each specimen marking a moment when some creature's story concluded. But it's also a library of persistence, evidence that even in death, life finds ways to continue its conversation with the future. Fossils are messages from extinct worlds, postcards from vanished ecosystems, love letters from ancient life to whatever forms of awareness might eventually evolve to read them. The gaps in the fossil record, the famous missing links that creationist critics like to emphasize, teach us as much as the specimens themselves. These absences remind us that preservation is rare, that most of life's experiments leave no direct trace, that the fossil record captures only a tiny fraction of the organisms that have ever lived. For every fossil we find, millions of creatures lived and died without leaving any permanent record of their existence. This incompleteness doesn't diminish the value of the fossil record, but enhances it. Each fossil becomes more precious because we know how unlikely its preservation was. Each species preserved in stone represents countless others that lived similar lives but left no permanent trace. The silence between fossils speaks of the vast abundance of life that has existed on Earth, most of it now known only to the processes that transformed it into soil, atmosphere, and ocean. But perhaps the most profound lesson of the fossil record is temporal. These ancient organisms lived in moments that were just as immediate, just as present, just as alive as your current moment of listening to these words. A trilobite crawling across the Ordovician seafloor experienced that moment with the same immediacy you experience this one. A triceratops grazing in a Cretaceous meadow was just as fully present in its moment as you are in yours. This realization transforms our understanding of both time and mortality. The billions of years of Earth history were not a vast, impersonal prologue to our arrival, but countless individual moments of lived experience, each one as immediate and real as any moment you've ever experienced. The deep past was not empty time waiting to be filled, but rich, abundant, immediate life, existing fully in each passing moment. From this perspective, extinction is not the opposite of life, but part of its rhythm. Every organism that has ever lived has contributed to the ongoing conversation of evolution. Whether or not it left fossils, whether or not its lineage survived, whether or not its contributions are remembered. The Permian animals that died in the Great Dying were not failures, but completed experiments, finished stories that added their own verses to the epic poem of life on Earth. This understanding makes every moment more precious, not less. If a trilobite's experience of an ancient sunset was as real and immediate as your experience of tonight's sky, then your current moment partakes of the same cosmic significance as any moment in Earth's history. You are not living in some diminished epilogue to the great stories of the past, but in the ongoing creation of those stories. Every sunrise you witness is indeed a small miracle, not because sunrises are rare, but because consciousness capable of appreciating sunrises is extraordinarily rare. In the 4 billion years of life on Earth, self-aware appreciation of beauty may have existed for only a tiny fraction of that time. The ability to understand the deep history of the sunrise itself, the nuclear fusion in the sun's core, the 8-minute journey of photons through space, the atmospheric effects that create the colors you see, represents an even newer and more remarkable development. The fact that matter has organized itself into forms capable of contemplating the cosmos is perhaps the most extraordinary development in the known universe. Stars have been shining for billions of years, but only recently has the universe developed eyes capable of seeing that light, and minds capable of understanding what it means. Galaxies have been spinning through space for eons, but only in the last few moments of cosmic time has consciousness emerged to map their movements and comprehend their significance. You are the universe becoming aware of itself, cosmic evolution, developing the capacity for self-reflection, the 4 billion year story of life on Earth arriving at a chapter where it can read its own history and potentially influence its own future. This is not a small thing or a common thing or a thing to be taken lightly. As you settle into sleep tonight, consider that you carry within your body and mind the culmination of every survival story we've explored together. The oxygen you breathe was once poison that nearly ended life entirely. The complex cells that make up your tissues evolved after catastrophes that eliminated simpler forms. The neural networks that generate your dreams emerged from evolutionary pressures imposed by millions of years of environmental challenges and mass extinctions. But you also represent something new in the story of life: consciousness capable of understanding its own origins and potentially able to influence its own future. You are both the product of 4 billion years of unconscious evolution and potentially the beginning of conscious evolution, the point where life becomes aware enough of itself to take some responsibility for its own continued development. The continuing story of life on Earth will be written by the choices consciousness makes in the coming centuries and millennia. Will we learn to live as conscious partners in the evolutionary process, guiding development toward greater complexity and beauty? Will we find ways to preserve the biological heritage that catastrophe and recovery have created over deep time? Will we become the ancestors that future forms of consciousness will thank for preserving the possibility of their existence? The answers to these questions are not predetermined. They will be determined by the choices made by conscious beings like yourself, choices that seem small in the moment but accumulate over time into the direction of evolution itself. Every decision to preserve rather than destroy, to create rather than consume, to cooperate rather than compete, becomes part of the ongoing story of life, becoming more conscious, more aware, more capable of taking responsibility for its own future. Tonight, as you drift towards sleep and temporary unconsciousness, you do so as a temporary carrier of consciousness in the vast stream of cosmic evolution. Tomorrow, when awareness returns, you will again become part of the universe, thinking about itself, life contemplating its own nature, evolution becoming aware of its own possibilities. The story continues. The thread connecting the first cells to us remains unbroken, and consciousness, for the first time in the planet's history, has arrived at a moment where it can participate consciously in writing the next chapters of the longest, most improbable, most beautiful story ever told. The story of matter learning to become aware, of chemistry becoming life, of life becoming consciousness, and of consciousness learning to take responsibility for the continuation of the miracle that made it possible. Rest tonight knowing that you are both an ending and a beginning, both the culmination of the oldest story on Earth and potentially the opening chapter of an entirely new story, the story of conscious evolution, of awareness taking responsibility for its own future, of life learning to guide its own development toward possibilities we can barely imagine. The continuing story is yours to write, and consciousness gets another chance, with every choice you make, to show what becomes possible when the universe learns to think about itself with wisdom, compassion, and care for the countless forms of life that made such thinking possible. And so we return to the question that began our journey together through deep time. What if I told you that you're part of a story so unlikely, so precarious, that it's almost miraculous you're here to listen to it? Now, having traveled through 4 billion years of catastrophe and recovery, extinction and renewal, we can answer that question with the full weight of cosmic perspective. You are indeed part of a miraculous story, but not because you're separate from the forces that shaped it. You are miraculous because you are those forces made conscious. Every mass extinction we've explored together didn't diminish the meaning of life. It concentrated it, refined it, made it more precious by making it more improbable. The great dying that eliminated 96% of species makes the remaining 4% infinitely more valuable, not less. The asteroid that ended the dinosaurs makes every mammal, every bird, every flowering plant a walking miracle of survival and adaptation. Mass extinctions reveal life's deepest truth, that consciousness, beauty, and complexity emerge not despite catastrophe, but because of it. The spaces between endings are where life discovers what it's truly capable of becoming. Every creature alive today, including you, represents the successful completion of the most rigorous survival course in the known universe. Tonight, as you settle into the gentle rhythm of approaching sleep, you can rest in the profound knowledge of life's resilience. For 4 billion years, life has faced challenges that seemed insurmountable and found ways not just to survive but to flourish. The same genetic heritage that carried your ancestors through ice ages and asteroid impacts, through poisonous atmospheres and acidic oceans, through volcanic winters and greenhouse catastrophes, flows through your cells tonight. You are part of an ongoing story that stretches from the first self-replicating molecules to whatever forms consciousness might take in the far future. This story has no ending because consciousness has learned to take responsibility for its own continuation. You are both the product of that ancient persistence and the author of its next chapters. As you drift toward dreams, carry with you the wonder of deep time, the knowledge that every breath connects you to billions of years of survival, adaptation, and the slow emergence of awareness from chemistry. You are the universe learning to think about itself, cosmic evolution developing the capacity for gratitude, life itself becoming conscious enough to appreciate the beauty of its own existence. Sleep tonight, knowing that consciousness, pondering its own origins, is perhaps the most extraordinary development in the history of matter and energy. In you, the cosmos has developed eyes to see itself, a mind to understand its own story, and a heart capable of feeling wonder at the magnificent improbability of it all. Rest well, fellow traveller through time. Tomorrow, the continuing story of consciousness awaits, and the universe gets another day to marvel at itself through your aware and grateful presence.